Anyone have any questions about anything? We're gonna do office hours this afternoon I will host office hours from noon to 3. I don't necessarily expect all your TAs to be there the whole time, or if Bruce can't make it for that whole time, that's okay. But I'll have the Zoom call open from noon to 3. So if people want some help debugging voids, we can do that. I'll remind folks that I think everyone now has their lab reports in. If you don't, just a reminder that your lab report is due this afternoon. So just make sure that you get that in. I'm going to talk today. So where are we in sort of lectures? We're wrapping up Lab 2 next week. So Monday, people will have their final Lab 2 checkout on Monday, Tuesday, people on Tuesday, Wednesday, people on Wednesday, which means Lab 3 starts for the Monday people on Monday. So it's a good time to introduce Lab 3. So that's what I'm going to do today, is sort of introduce and motivate Lab 3, and probably not get into too many technical details of Lab 3 yet this lecture, just sort of talk about what it is and what the goals are. Before I do that, I wanted to wrap up just a couple of thoughts about DMA from last time. And what had occurred to me that I didn't really talk about very much, and that I probably should have, is if you want to start messing around with DMA, how do you actually start? You know, there are certain sort of ways that you start with new things. If you get a new microcontroller, the first thing that you always do is blink an LED, right? And then you get it to say hello world. If you're messing around with DMA, the place to start is to make 2 arrays, put some information in one array, maybe a string of characters that says something like hello DMA, and set up a DMA channel to just move the data from that array to the other array, and then print out the contents of the second array. That's the first thing to do with DMA. So you point at your source address will be the beginning of your starting array. Your destination address will be the other one. You'll specify the size of the chunks in which to move the data and the amount of data to move. And you should see the data move from one array to the other array. Basically, a DMA version of memcopy is the first thing to implement. And then once you've got that figured out, you can start peeking through data sheets to figure out interesting addresses in memory to set up DMA channels to and from. Right? So to get started, the address is just the addresses of the 2 arrays. But then once you've got that figured out, you can say, I wonder what the address of the analog to digital converter is. And you set that as your source address instead of the array that you were testing as your source address. And you start moving information from more interesting places. So in any case, that's just how that's how you start with a peripheral like that. That's sort of the DMA version of hello world, is one array to the next array. Are there any pending questions about DMA stuff right now? We might do a lot of that content again in maybe a couple weeks as people get started with final projects, if people would find that useful. But does anyone have any pending questions at the moment?
I have a question. Could you go over a little bit about what like the constraints we have for the final project are because of COVID? Because I saw on the website, it's like, I don't know, I guess I wasn't really sure like how I'm gonna approach my final project, knowing that I have to do it like with the PIC32 like online and that kind of thing.
Yes, I can talk a little bit about that, and I think we'll have a longer discussion about that in sometime in the next few lectures. But I'll briefly say, this semester, for your final projects, I'd say you're free to do anything that you would like within the constraints of the infrastructure that's set up. So we have some hardware set up for you already. Everything audio is set up for you. You have the pan tilt servo assembly set up for you, the TFT display, and the connection to the lab PC, which opens up the opportunity for final projects of a few different varieties. Any audio related final project is fair game. Any computer graphics related final project is fair game. Networking related projects are likely fair game. If you wanted to if as a part of your final project, you wanted to interface your PIC32 with some other piece of hardware, I'm not going to say you can't do that, but there are going to be limitations on the complexity of the hardware with which you're interfacing. Because basically, I get to play the role of lab technician. for those sorts of projects where you have to tell me, hey, I want you to hook up this pin of this device to this pin of the PIC32, and you specify all of that. And it has to be a simple enough interface that it doesn't require sitting in front of an oscilloscope at the bench for a week to get it figured out. Okay, but if it's some very simple SPI device, for example, that you want to hook up to the PIC32, I'm open to that, and we can talk about those sorts of projects. But generally speaking, it's anything that you want that uses the infrastructure that's in place. So think the sorts of things that we're doing in lab, extensions of that or branches off of that. Or if you use external hardware that's relatively simple, at least for this semester. And like I said, I think next week I think it'll likely make sense to devote most of a lecture to just kicking around ideas, because as you've observed, this is a weird semester, and exactly what's fair game and not fair game is maybe not obvious. So we'll devote some time as a group to kicking around final project ideas. Does that answer your question, at least approximately?
Yeah, that sounds good. Thank you.
Okay. Okay. Any other questions? Okay. In that case, I'm going to get started. I'll share my screen here. So what I want to do today is just introduce and motivate Lab 3. Lab 3, you may, or oops, did this share? Share. There we go. You see that now? Yeah. Can't see anything? Okay, okay, thank you. Yeah, my laptop's been acting up a little bit this morning, so I'm not sure exactly what's going on. In any case, Lab 3, you may or may not recall, is the audio spectrogram lab. I mentioned on the first day of lecture that one of the reasons that all of these labs are what they are is because I find them interesting. They were chosen for a number of other reasons, but one of the primary reasons that a lot of these are what they are is just because they're cool. I think they're cool, which makes them easier to teach and hopefully more fun to learn. So I find all the things that we do interesting. I have to say, I think this audio spectrogram is my favorite one. And the reason for that is we're going to talk through exactly what you're going to put together in this lab, but you are going to build a device that it's going to produce real-time audio spectrograms, which means you can play sounds into it and see the frequency content of those sounds. And what's so fun about it is you can find a lot of stuff that surprises you. Like you can find certain sounds and you listen to it and you think you have a guess of the frequency content of that sound. And then you actually look at the audio spectrogram and it's different than you expected or way more complex than you expected, or there are strange patterns that you find in there. So I find it very addicting in that regard. There is evidence of how addictive this is on the lab write-up for this assignment. There's like something like 10 examples, and it's just because I spent like 2 days playing with this thing because it's really addicting. So I think you'll find it really fun. But in order to get the most out of it, I want to talk for a little while and at a high level about what it actually is that you're looking at when you look at an audio spectrogram. This is stuff that for some of you might be review, and that's okay. But I want to make sure that everyone appreciates what it is that they're building so that when you build it, you can really enjoy it. So I want to start this discussion at, I guess, from as close to first principles as I can manage as someone who's not medical or doesn't study physics, but is just an engineer. But I want to start from the perspective of what exactly is sound and how do your ears work. And I want to talk briefly about how your ears work, because it turns out microphones, should be no surprise to you really, but microphones work pretty similarly to your ears in a lot of ways. So what is sound? Sound is, it is vibrations propagating through some medium. So the way that sound is produced in the case of speaking in human voice is the air in your lungs drives vocal folds that are in your larynx, which are essentially little membranes that vibrate. Those vibrations set up pressure waves in a medium. In the case of human speech, that medium is air. So those pressure waves propagate up your throat. You can modulate them with the stuff above your larynx, so things like your cheeks and your palate and your lips and your tongue, you modulate those pressure waves and then they leave your mouth. And they propagate out through the medium, out through the air. So for us, the medium through which sound propagates is air. For whales, the medium through which sound propagates is water, obviously. In the case of the sun, there is sound propagating through plasma as the medium. And in each of these media, that sound propagates at a certain velocity. And the velocity at which those waves propagate through the medium depends on the properties of that medium. In particular, it depends on the density of it and the bulk modulus of it. Bulk modulus being the resistance of that medium to compression. So sound, as it turns out, travels way faster in water than in air. In air, it's something like 340 something meters per second, I think. In water, it's something like 1,400 meters per second, if I recall. I might have those numbers slightly off, but a few times faster in water than in air. So when you speak, you're creating pressure waves. How are those pressure waves actually received on the other end by the person that you're talking to? Well, they propagate into the listener's ear, and in that ear, you have an eardrum, which is a little membrane, and the pressure waves, they're very sort of mechanical, right? They can move things. They set up oscillations in your eardrum that communicate the pressure waves from the air media to an inner part of your ear that is fluid filled. There's an inner part of your ear that's filled with fluid called cochlear fluid. And your eardrum sets up vibrations, puts waves into that cochlear fluid. In that fluid, you have small hairs, and the hairs are bent by the waves through the cochlear fluid. The bending of those hairs, much like piezoelectrics, set up electrical impulses that are communicated up your auditory nervous system into your brain. And in your brain, they are decoded all behind the scenes, totally separately from your conscious mind, into meaningful words, right? So it's an interesting process, I think. And the reason I'm talking about all this is because we are using devices to do the listening. We're using microphones, but microphones in a lot of ways work pretty similarly to the way that your ears work. How does a microphone work? Well, there's some, as before, sound is produced by setting up some sort of vibration in the media that propagates. A microphone has some sort of a membrane in it that the sound waves will cause to oscillate. Those oscillations set up small amounts of electrical current. Piezoelectrics, you can turn mechanical motion into a little bit of electrical current. So those oscillations set up some electrical current. We amplify that current, and if we put that through a small resistor, we can sample it as voltage, right? So, and then we communicate those voltages to whatever is playing the role of the brain, some sort of a CPU. In our case, it's the PIC32, and we do processing of those sampled voltages on the PIC32. So we can look at what this actually looks like. So what I have set up here is the picoscope. I've joined this Zoom call from the lab PC, as I often do. And in this case, I've set up the oscilloscope probe to the audio input jack on the remote learning external PCB, right? So the headphone, I have an aux jack plugged into the headphone jack of the laboratory PC, and I am sampling the voltage on one of the pins of that headphone jack. Ordinarily, this voltage would be sent into your headphones to drive another membrane to set up pressure waves very near to your ear to send into your eardrum. In our case, we're just sampling those voltages so that we can see what these sound waves actually look like in the time domain. So what you're looking at as I speak is the voltages induced by the vibrating membrane in this microphone as I talk. And you've all seen stuff like this before, right? Like, this is no surprise to anyone. I still do. So I'm a person with a very low threshold for wonder. I get, my sense of wonder is induced by like pretty dumb things. I get like, I still get a real sense of wonder by looking at this type of thing, because you are peeking at hidden complexity. And I love I love stuff that does that. You know, this system that evolution has completely obfuscated a lot of the complexity of this whole mechanism away from your conscious mind. So all of this complexity, as you go around your daily business, is obfuscated from you. You don't actually notice it. But when you have the opportunity to sort of peek inside and see what's actually going on, there's a lot of complexity going on here. And what we're seeing, not surprisingly, is a bunch of what looks like a bunch of sine waves additively combined, right? And that should be no surprise, really, because where are these voltages coming from? Well, the sound waves are setting up oscillations of some membrane that's setting up currents. Those currents are being turned into voltages. We're sampling those voltages. So if there's something that's oscillating, it makes sense that if we're tracking the amplitude of that oscillating thing, we're getting some sort of harmonic motion out, some sort of oscillatory motion out. And the question is, you know, what frequencies are represented here? What range of frequencies are represented here? You'll all recall from at this point, probably like 10 different classes, that you can take some arbitrary time domain signal and do what essentially amounts to a Fourier decomposition of it and break that signal into linear combinations of pure sine waves. So the question to ask is, for a human voice, what's the range of sine waves that's required in order to perfectly reconstruct a voice?
Hunter,
Yeah.
could you just do a constant vowel, like put an E into it? E.
E, O, A.
So you could see a clear repeating pattern in there.
Zoom's
Now-
filtering my whistle.
Now make a hissing sound like a tss.
Noisy. So and this is true of the how do I want to say this? The vowels are very clearly linear combinations of sine waves of relative to some other sounds, low frequencies. When I hit consonant sounds, there's a lot of high frequency stuff in there. Right? And we can get a sense of this. So if you wanted to answer this question of, all right, what frequencies are represented here, a way to do that is to look at the FFT of this signal, which this oscilloscope lets us do. And as I'm talking, so you guys all know what an FFT is, but I'll just remind you that we have transformed this signal from time domain to frequency domain. So the x-axis now is frequency in hertz. This goes from 0 up to 5 kilohertz. And then the y-axis is the amount of power at each of these frequencies. So as I'm speaking, you can see the power that I'm putting into all of these different frequencies. And you can see that for me and for my voice, this range makes it a little hard to tell, but for a male voice, the fundamental frequency tends to be around somewhere like 100 to 120 hertz. And then you get harmonics that go up higher. So if I say something like E, you can see that we're exciting some frequency somewhere right, maybe around here, somewhere around 100 hertz. And then if I hit a consonant sound, it kind of looks like broadband noise, really. It is broadband noise, right? It's just a hiss. It's like white noise. So this is kind of interesting. And it's worth thinking for a minute about what is this relevant range of frequencies for human voice. I said that for male voices, it's somewhere around 100 to 120-ish hertz. In female voices, the fundamental frequency tends to be about an octave higher. In children, it's around 300 hertz or so. So we're talking about ranges of frequencies that are in the few hundreds of hertz up to, you know, if you want to get a few of the first harmonics, maybe up into a few kilohertz for human voice. So why is this interesting? Well, to your consciousness, that is wickedly fast, right? I don't actually know what the update rate of human consciousness is. Like, I don't know how many different events you can consciously register in a second. Maybe that's been, I don't know what that number is. Bruce says 5. Is that right? Is it that low? In any case, so this is something is happening here that is orders and orders of magnitude faster than your conscious brain is updating. However, the PIC32 is running at 40 megahertz. And these signals are happening at the hundreds to maybe a few thousand hertz, right? So to the PIC32, these processes are really slow, like hundreds or thousands of cycles of what am I trying to say? Between audio samples, right? You have hundreds or thousands of cycles to spend to do whatever you want before you have to go and leisurely get the next audio sample. Because for the PIC32 operating at, you know, it's thinking at 40 million times a second. And this process is occurring at a few hundred to maybe a few thousand times a second, which makes, this is why I find audio related microcontroller projects kind of interesting, because you can do real-time stuff with audio. You have plenty of time between audio samples to do math and to do processing, right, which is what we're going to do in lab 3, so that you can do things like real-time visualization of audio as people are talking or as sound is being generated, which seems almost miraculous to my conscious mind because I'm operating at such a slower rate, but it's easy for the microcontroller. It's kind of fun in that regard. This would be harder for, you know, if you think about something like maybe something like radio, right? Radio, we're talking about maybe tens of megahertz frequencies. That's getting up to the same order of magnitude as the processor, which means you have less wiggle room between your samples, if you have any wiggle room at all between your samples. So it's harder to do interesting real-time processing of things like radio on a microcontroller because the relative speeds of the two processes are about the same. In the case of audio, it's orders of magnitude slower than the PIC32. So we have time to do stuff like an audio spectrogram.
Hey Hunter,
Yeah.
what do you mean when you say the relative speed of radio and audio is? I get the speed of the PIC you mean the clock cycle, but what do you mean the relative speed of radio or audio?
So what I mean is, if we look at the FFT that's bouncing around on the screen right now, what this is showing is if we decompose the signal of my voice into a linear combination of a bunch of sine waves, this is showing us the amplitude of sine waves at different frequencies. And what it's showing us really is that in order to fully capture my voice, we need to be able to what's the word I'm looking for? Reconstruct sine waves as high frequency as maybe 3 to 5 kilohertz. With radio, if we were to look at an incoming radio signal, say we were looking at we had an antenna outside and we were just picking up FM radio transmissions, right? And we were doing a similar thing where we were looking at, okay, here comes this transmission. What's the frequency content of this signal? Doing an FFT, much like we're looking at here. What we would see is that in order to reconstruct the FM radio signal, we would need to be able to resolve sine waves as high frequency as, 90 megahertz or so. Which, if you remember from some signals class, in order to actually do that, the Nyquist sampling theorem says you need to sample that wave at least twice that fast. So if you want to resolve signals as fast as 5 kilohertz, you need to sample that at least 10 kilohertz. So in the case of radio, if your signal has a 90 megahertz carrier wave, you need to be able to sample that at least twice that fast, which is hard to do on a processor that's running at megahertz itself.
Is it hard or is it impossible?
Well, at a certain point, it becomes impossible. It depends on the frequency of the carrier wave that you're trying to resolve. Bruce, do you have anything you want to add to this?
Well, if you're thinking of the PIC32 specifically, yeah, sampling a radio wave in real time is impossible, although you can do this weird thing called baseband subsampling. But yeah, I mean the whole hope here is that your A to D converter can take enough samples that you can resolve the signal.
So sorry, just a quick follow up then. So if our phones and our computers, because they do get radio waves in terms of, or not computers, but maybe, or even computers, they get radio waves when we call someone, etc. Right? So their ADC or their ADCs or DACs are working much faster than the PIC, then I'm assuming?
No, that's all done analog.
Oh, right. Okay.
And then like, I also had a question, like, so like the fastest phone processor might be like a couple gigahertz, but then like if 5G, that's 5 gigahertz. So, like, is that also all done in analog, or like if you wanted to have like internet connection on your phone from anywhere?
All analog, as far as I know. Can you confirm that, Bruce?
As far as I know, it's until you get to the first down sample. Do you know about mixers? If you mix the 5 gigahertz down to a lower frequency by doing a multiplication with a nearby frequency that you generate locally, once you've mixed it down to a megahertz or less, then you can use digital stuff with it.
Okay, thank you.
So with all this being said, so then what's an audio spectrogram? So what this FFT is showing us right now is for a particular moment in time, right? This is updating all the time. So for a particular moment in time, it's telling us it's gathering some amount of samples. In our case, actually, it's gathering, let's see, 512 samples, and it's gathering those samples at 5 kilohertz. It's gathering 512 samples and then creating this plot. It's doing an FFT to represent the frequency content of those samples, and then it's gathering another set of samples and doing it again. So we're seeing effectively snapshots of frequency content with time. What a spectrogram does is reduce this plot that we're looking at here, this FFT, to one dimension. So we keep this X dimension, okay, where we have some particular dimension that represents frequencies. And then instead of representing the amplitude or the amount of power at that particular frequency as the amplitude of some plot in a y-axis, we instead compress all this information to one row of pixels, where each of the pixels in that row is colorized according to the amount of amplitude that appears in the FFT at that particular moment in time. So perhaps if we were to use the convention that, you know, a lot of amplitude is colored red and not much amplitude is colored blue, then we would see, as I'm speaking, you know, you can see I'm putting quite a bit of power into somewhere around here. So if this were all compressed down into a row of pixels, we'd see a red spot right here where I'm putting a bunch of amplitude into these frequencies, and then some blue ones here where I'm not exciting these frequencies very much, etc. So this all gets compressed down into one row of pixels, and then each of these snapshots is the next row of pixels. And then the next row, and then the next row, and we build all these up across the screen so that you can see the time history of the frequency content of a signal. We looked at these in lab 1 for bird calls, right? The time history of the frequency content of a signal. And then in our case, what we'll do when we get to the end of the screen, I'll show you this in a moment, is go back to the beginning and start drawing over it, much like an oscilloscope does. So you end up being able to watch the frequency content of any sound that you play into the PIC over time and in real time. So just to give you a sense of this, let me open up the camera here. And I have this programmed with the audio spectrogram. So what you're seeing, the same information is being represented on the TFT display as is being represented on the bouncing FFT behind it. All that's happening is that each of these FFTs gets reduced to a single row of pixels that slides across the screen so that we can see how the frequency content of my voice changes with time. And I'm also printing out the max frequency of my voice. So let's see, if I do something like E, you can see, as I said, E, I'm exciting a main frequency somewhere around. Let me change the frequency range of this so it's a little easier to see. Also gives me the opportunity to show you the Python code that you're going to be putting together. So I'll open up the PowerShell.
As an aside, there's enough information in the spectrogram that a human can be taught to understand speech by watching the spectrogram.
The other interesting thing related to speech is this goes back sort of to the update rate of consciousness, maybe somewhat. So I mentioned that these kilohertz rate processes are way faster than your conscious mind is sort of picking up in real time. An interesting thing about speech that I learned in preparing to talk to you about this stuff today is there's this question of what's the bit rate of human language? So as I speak, what are the amount of bits per second being transmitted from me to you as I speak? It turns out that this is a weirdly universal number. So there are some languages that have more syllables per second. Italian is a fast language in that sense. There are a lot of syllables per second. German is a relatively slow language. There are less syllables per second than Italian. However, in both of these, and weirdly for like pretty much all languages, it appears as if the bit rate is about 39 bits per second. So as two people communicate with one another, the rate at which information is being transferred is somewhere around 39 bits per second. It's just kind of it's a weird, I don't know what is, well, I don't know where that number comes from. I don't know what the bottleneck in the process is. I don't know if it's the processing. I don't know if it's the actuation of the musculature in the face. I don't know. I don't know what it is, but it's interesting that it's universal. Spectrogram. So the user interface that you're going to make for this lab is quite a simple one as compared to like the Boyd's lab. There's really only one degree of freedom here, which is, you can see on the left side of this screen, we have the range of the spectrogram in hertz. So it goes from 0 hertz down here up to, in this case, just below 5,000 hertz. And you're going to create a spectrogram that allows for you to change that range. So I'm going to change this now so that the top frequency is somewhere around 2,000-ish hertz. The reason it's nice to be able to do this is depending on the sound that you actually want to observe, you may want to reduce that range or increase that range. So I mentioned that for human voice, for my voice, this is probably about the range that makes sense, right? We can see some stuff is happening up to around maybe a kilohertz, but we can see my fundamental, and then we can see a few of my harmonics here. If we were listening to bird calls, which we can do in a moment, I would turn that frequency range up much higher because they operate at higher frequencies than I operate. If we were listening to whale song, it makes sense to turn it down lower because they tend to sing at lower frequencies. Or elephant rumbles, elephants will rumble down to almost infrasound levels, pretty much undetectable by humans, around 10 hertz or so. Elephants rumble and they can pick it up. So it's a method of long distance communication. But in any case, the point that I'm making is that the information shown here and the information behind here is the same, except that this is retaining the information of a bunch of previous FFTs that are bouncing behind the screen here. Questions about this?
Do an E again. You can see 3 bright lines there.
A lot more there.
Higher frequency.
That's just broadband noise. It's interesting, right? So let's look at some, let's do this. I want to look at some bird calls and some other, I want to just show you some of the stuff that I found surprising and interesting. So I'm going to put the time domain stuff behind the spectrogram so we can kind of see both. And then let's look at, let's see here. Let's look at the Northern Cardinal song, because by now you all are pretty much experts in the Northern Cardinal song. So now the question is, will you actually be able to hear this? You actually might not be able to. Let's see, can you hear this? Probably not, because I can't. Okay. Well, let's just look at this. So, okay, so we've got, sorry, too many stuff on the screen. Time domain back here, frequency domain here. I'm going to play a song. What you can see is familiar looking time domain shapes in the background. As a part of your Lab 1 report, you were asked to include these oscilloscope traces of the swoop and the chirp amplitude modulated. And if we play the actual songs of these birds, let me play another one and then I'll shut up so we can actually see it. So you see familiar looking amplitude modulated envelopes in the background with maybe a little bit more subtle amplitude modulation than we did in lab. It's hard to pick that up with your ear, but you can see it on the oscilloscope. And then on the TFT display, you can see the actual frequency sweeps that are taking place. So the spectrograms are interesting because they show you, they take a time domain signal that looks kind of like a mess and make it very clear what's going on. It's kind of interesting. So let's see, let's play, let's do this. I'm going to turn this down. Let's listen to a whale song.
So I think it's going to be, it's updating something like at 10 spectra a second, something like that.
Hunter, there's the optimize for shared video option in Zoom when you share your screen. That might make it smoother for people.
Okay, okay. You guys hear this now?
Yeah.
I find this just endlessly fascinating. The other interesting thing to look at is stringed instruments. So let me pull up a video of someone just playing a scale on something like a piano. Let's see. Let's do this. So I'm not sure how easy it is to see, but what you're seeing, my voice is going to cover it up here in a second, is the stringed instruments have perfect harmonic stacks. So someone strums a note on a violin and you see the fundamental, and then evenly spaced the whole way up, you see all of the higher harmonics in a perfect stack. Just, I mean, maybe it's just because I don't know much about music, but when I saw that, it's very surprising. It's so ordered, so nicely structured, which makes things like, let's see, let me play like a Bach cello suite. It makes that kind of stuff look so interesting. Golly, my computer is being slow. Let's see. So you can see the fundamental and the harmonics going up, and it changes as the notes change. Let's see, we have 2 more minutes. Let's just do one more. The other thing that I found interesting to look at, you guys will find lots more. I'm just showing you a few. Was opera vocalizations? Because the notes are quite pure. Let's see. Anyway, we're out of time, but I think you'll find it really interesting. Open up YouTube and just start playing stuff into it, and you're going to surprise yourself over and over again with the frequency content of these various things. Any questions from anyone?
There's a whole art form, which is to attempt to draw recognizable pictures on a spectrogram. So you manipulate the sound so that what comes out is a happy face on the spectrogram, for instance.
That sounds like a final project.
Oh, it is a particularly twisted kind of mentality that does this.